Let us now focus on the output layer. It is named Gaussian connections, and it is not a classical layer. It works as follows. Imagine that you apply the network to an image. In the penultimate layer, you obtain a vector of size 84. This layer is composed of 84 neurons. Then the output layer computes the above quantity, which is the L2 norm of the difference between the vector output by the penultimate layer and pre-specified vectors wj, for j ranging from 0 to 9. Why do we consider 10 vectors w? Remember that our task is to classify the images according to the digits which is written on them. Since there are 10 classes, we would like to have a vector representing each class. So, assume that we succeeded in finding good vectors wj, which correctly represent the number j for j ranging from 0 to 9. If we have these vectors, we can compute the distance between the penultimate layer of the network, a representation of the input image, and each vector. We are going to classify the image based on the smallest distance to all vectors wj. If the vectors wj are correct, the representation output by the network for an image whose true label is j should be close to wj. Another way to view this computation is the following. Imagine that the images of class j can be represented as vectors of size 84, normally distributed over a mean wj with a covariance matrix identity. Then, the L2 norm between the vector produced by the network and wj is nothing but the negative log likelihood of the Gaussian distribution. So, basically, we are just computing probabilities expressed as negative log likelihood that an observation belongs to each class j. One major question now is how to choose the vectors wj belonging to -1, 1 power 84. Basically, we want to find a stylized representation of each class in the form of a vector -1, 1 power 84. One way to do that is to draw a stylized version of the digit in the form of an image of size 7 by 12 equal 84, with black and white pixels corresponding to -1 and 1 respectively. These representations are not learned, they are fixed once and for all before the training of the algorithm. We therefore have access to the wj, which are the vectorized, flattened forms of the images. This method may seem strange to you. Nowadays, we would probably use one-hot encoding for the labels of the image with the crossentropy loss that we have seen in the first session. These techniques are common now, but not in the early 90s. Indeed, it is stated in the paper that one-hot encoding does not work with more than a few dozens of classes, since it requires output units to output zeros most of the time, which is difficult to achieve with sigmoids. Indeed, obtaining exactly zeros with sigmoids is impossible, and nowadays we would probably use ReLU instead. Anyway, in the early 90s they used the hyperbolic tangent with the coefficient a and alpha defined as follows. They are chosen to satisfy these equalities, that is, to help preventing saturation and allowing the output to be close to -1 and 1.